as chi-squared goodness of fit. So same problem. As a goodness of fit. Clearly in the long run we do it only one way, and for this particular one you choose whichever one you wanted. You can do it either way, but right now we're going to do it as goodness of fit. There's the same information. Alright, with goodness of fit, as with any of the two chi-squared problems we have, it's quite common that we're forced to use words to describe the hypothesis, so I'll do that here. Alright, so the null hypothesis in this case will be that the coin is unbiased. And of course that the alternate coin is biased. In general, the null hypothesis will specify or imply a given probability distribution. And of course the alternate then will be not that particular distribution. What distribution we have here? Well, we have a simple distribution. The probability of a head is a half, probability of a tail is a half. The next step is to draw a table with our information. First column will be O, which we'll see in a little bit, stands for observed. So O will be observed frequency or count. This is the information that comes from the sample. It's the observed values. And next, going to have a column little p for probabilities, basically from the null hypothesis, either specified or implied. And our third column, E, is going to be for the expected frequency or expected counts, and these expected values do not have to be whole numbers. So the observed frequency in this case, right, remember we had heads and tails. The observed frequency would be 45 for our sample for heads, and therefore we must have had 55 tails. Alright, total sample size of 100. Probabilities applied or specified by the null. The coin is unbiased, and the probability of a head is a half, probability of a tail is a half, and of course the total sum of the probabilities in any probability distribution is equal to 1. Alright, and then expected values or frequencies, same formula as we use for the binomial in 214, that's n times p. N in this particular case is the 100. Alright, so we're going to go 100 times 0.5, and we expect to see 50 heads on average, and of course the same thing for tails, 50 tails. Make sure that we understand that we have 100 here and 100 here. In other words, whatever the observed frequencies add up to, the expected frequencies must add up to the same thing. Alright, why are we doing this? Well, remember a little while ago I said that a goodness of fit, you're going to compare some sample observed data to a given probability distribution. We wanted to essentially know, is this observed distribution equal to this probability distribution? Since there's a difference in scale here, we want the two to have the same scale. All right, and the easiest way to do that in the long run is to inflate the probabilities so that they have the same total. So the way to do that, of course, is to multiply through by 100. All right, and so now the observed and the expected have the same scale. We want to know if the observed distribution is, in a sense, in the population equal to the expected distribution. Alright, at this point, and we won't see this in a little while, but all expected values, which are n times p, must be greater than or equal to 5, or the approximation to the chi-squared is not good. Alright, just like we had in the binomial, you might remember, to approximate the binomial with a normal, we needed the expected values to be greater than or equal to 5. Alright, here both expected values are greater than or equal to 5, so we don't have to worry about it. But down the road, we will have to worry about it, but we'll see that later. Okay, so now we go ahead and concern ourselves with degrees of freedom. Degrees of freedom for the chi-squared is the number of categories in the probability distribution. Number of categories minus 1. There are just 2 categories here. Simplest of all chi-squared problems. Alright, so now we can draw our distribution. Remember, the chi-squared distribution starts at 0, climbs quickly, and then trails off to infinity. So let's call this our chi-squared with 1 degree of freedom. We use an alpha of 5%. And we're going to go to the chi-squared tables and find that value, the critical value. So here's our chi-squared table. 1 degree of freedom, the first row, alpha of 5%, and we have a critical value of 3.84. As with any hypothesis test, where the alpha is, we will reject the null, and where the alpha is not, we say do not reject the null. Okay, so that's how our decision rule will run. So